Welcome to the next edition of the zkVerify Hackathon live stream series. Got a good one for you today. Got Luca Giussani here. He's going to go through one of the coolest things that we can do with the Web3 EVMs and zkVerify. I'll introduce Luca in a second. I just wanted to, actually, I'm going to introduce you right now so you can say hi, Luca. So Luca's a software engineer, been at Horizon Labs for 3 years. He does development on the cryptographic side. So, we got all these white papers and ideas of zero knowledge proofs that are heavy duty cryptography papers. Somebody has to convert that into working code. Luca is our main guy that does that. Really good in Rust, Solidity, JavaScript, and we'll talk a little bit about what he can present in a second. But Luca, thanks for joining us.
Yeah, thank you, Rolf, for the introduction. And today we are gonna see in detail how it's possible to develop a on-chain zk app, which uses zkVerify for performing verification of zk proofs in an efficient way.
Wonderful. Let me give everybody a quick overview of what our hackathon is, and then we'll get started and do that. So our hackathon is the zkVerify zk app and infra builders hackathon. It's available on DevFolio. 2 weeks from now, the projects are due, so that's December 10th. We've got a lot of great information here about what it is that you can do with zkVerify, what we're looking for from the hackathon, all sorts of stuff like that. I'm happy that we've got some solid sponsors and $26,000 available in prizes. We've got really high quality judges and speakers from all aspects of the ZK space. Horizon Labs is a sponsor, Hyperbridge, ZK Pass, Sindri, and then we got a bunch of really useful ideas in the frequently asked questions. So put a lot of time and effort into that. And one of the things that I do want to highlight is that if you got an idea and you want to talk about this with me, with developers, I've got experience in building businesses, doing all sorts of different things, product market fit, that kind of stuff. Happy to talk with you about the different types of things that you might want to build. If you got specific questions on how to integrate with zkVerify, then we actually had a couple previous live streams that on developer tools that Steve Rushby did on how to do a decentralized proof verifier for Web3 and browser-based games. That was earlier this week. Had some of our builders and sponsors talk about how you can win their specific prizes. And today is the one that I've really been looking forward to, which is to have Luca talk about how to integrate zkVerify with an EVM Smart Contract app. And you might say, well, why do we even need that? Because, there's the BN254 elliptic curve on every EVM, and you can just verify your ZK proof there. Well, you need it because since that BN254 precompile was put on Ethereum, there's been like 7 years, because we've done that in 2017. There's been 7 years of zero knowledge proof advancements. There's so much advancement in this space. There's the ability to use ZK virtual machines, ZK coprocessors. There's new elliptic curves. There's Starks. There's FRIs. And every week I turn around, somebody's making a new kind of ZK proof. You got to verify the proofs. And so zkVerify is the leading blockchain that's a public, decentralized ZK proof verification platform. So I see in the future, all these different ZK proofs can come together and be verified publicly, high speed, low cost on zkVerify, and then we can share them through the Hyperbridge bridge to every other blockchain that's out there. And so today, Luca has a specific demonstration, and we're going to quickly get into some serious technical code review, and I'm going to be quiet while Luca does that. But the idea is to have a Web3 application, a smart contract that wants to be more secure. So he's going to take Groth 16, not using the BN254 precompile, but using the much more secure BLS 12.321 elliptic curve. verify that on zkVerify, and send that verification receipt back to the zkVerify smart contract on the EVM and make it available to the application. And this same exact design pattern can be used for the other types of proof verifications that somebody might want to do. So right now, there's developer teams that are developing proof verifiers for zkVerify for Halo 2, for Starkey, for Plonky 2, and the Succinct SP1 Stark proof. And we're just going to keep adding more and more as we go along. So Luca, please go ahead and share your screen and start talking about how we can do this stuff.
Yeah, so I'm sharing my screen. Okay, should be able to see it now.
Yeah, let me pull that onto the stage here, and we will get going.
Okay, so Rolf already told everything basically of what we are doing. But yeah, to reiterate, we are gonna see how it's possible to build an on-chain zk app. So what do we mean by that? So it's an on-chain app, so part of the logic lives in a smart contract on-chain, more specifically in a Solidity smart contract, which runs on EVM. And the logic of this app requires checking zk proofs. And more importantly, this checking of the proof must happen on chain. So, of course, this is already possible on EVMs. If you stick basically to a handful of proof systems which use elliptic curve cryptography on a specific curve, which is the BN254. And there are a lot of applications which already do this, either for privacy, so for the zk properties of zk proofs, or for, let's say, computational integrity. So to be able to verify a lot of computation without recomputing it, so in an efficient way. However, all this system must, let's say, jump through hoops in order to bring their proof on chain, because basically you are restricted to only a few proving systems on a specific curves. So here enters zkVerify, which instead being a blockchain which is specialized on verifying zk proofs, offers a much wider range of possibility.
So Luca, I just want to interrupt you for a second.
Yes.
Is it possible you can make these words look a little bit bigger on the screen? It's just with the resolution, sure. I'm having a hard time seeing them. That's already better. Maybe one more. No, that's good. I think that's good right there. Sorry to interrupt you about that. I just wanted to make sure that everybody could see the actual words that you're going through.
Yeah, thank you. Yeah, so, okay, to be more concrete now, we are developing a very simple app. I mean, the logic will be almost silly because, okay, the objective of this live stream is to see, let's say, the architecture of the app. So all the components, how they interact with each other. And we don't focus on the actual logic of the app in order not to overshadow the let's say, the architectural discussion. And so our app will require a user to generate a zk proof that he can actually compute he knows the factor of the number 42. So it's, let's say, an extremely trivial application. And then the user will have to generate this proof and submit this proof on chain to the app smart contract. And if the verification is successful, then basically the smart contract will emit an event. So this is the simplest, let's say, zk app, but it contains all let's say, the elements which, the basic components which every zk app actually has to implement.
So I'm just going to jump in here and say 42 has a special reason with Horizon. So when we first started Horizon, we wanted people to be able to have secure nodes, to have copies of all the Horizon code all over the world. And we decided that they needed to own 42 Zen to be able to participate in the secure node. So that was way back in 2017 that we decided that. And so secure nodes and then super nodes have become an important part of Horizon ever since. So, of course, 42 from the Hitchhiker's Guide to the Galaxy, it's always the answer. So, sorry to interrupt. Thanks.
Yeah, that's a nice trivia. And okay, all the code, you can access it inside zkVerify GitHub. It's on this freshly created repository, zkVerify EVM dApp example. At the moment, it lives in its own branch initial imp, but right after this live stream, I will merge into main. So for the moment, if you want to see the code, you have to switch to the initial int branch. And so, okay, maybe we can start from, let's say, analyzing the workflow of a zk app, which wants to use zkVerify.
Can you zoom in on the picture too a little? It's just
yeah.
Perfect.
Okay, so this example uses a specific application, which is Polygon CDK, which, as you may know, is actually L2 on Ethereum. So Polygon offers this CDK in which you can spin up your own L2, which settles on Ethereum by posting zk proofs. So it's a very complex piece of code, a very complicated zk app. But we will see that the components are always the same. So here, our app of chain component is this Polygon CDK, which receives transactions from the users, bundles them together in blocks, and generates zk proofs for proving the correctness of the transaction. And in the original Polygon CDK, these proofs are directly sent to a smart contract on Ethereum called, here, I don't know if you can read, but it reads validium.sol. So it's the Polygon CDK smart contract. And then these proofs get sent to another contract, which is a flonk verifier contract, which, guess what, uses the BN254 curve. And so originally, the Polygon CDK directly sends proofs to Ethereum for settling them. However, this restricts the cryptography it can use, and also sending this proof is quite expensive, and so if smaller L2 rollups have a hard time justifying this expense if they don't have a high enough throughput. So as one of our first exercises, let's say, we converted this Polygon CDK to instead use zkVerify for settling the proofs. So how the workflow changes. So the Polygon CDK stays basically unchanged, except that instead of sending the zk proof to Ethereum, it sends this proof to the zkVerify main chain. Specifically, zkVerify offers several proving systems. Among these is the flonk verifier, which is the one used by Polygon CDK. So there is this method inside zkVerify which checks the proof. If the proof verification is successful, then it gets included into a block, and an event is emitted, which allows the client to know that his proof has been successfully included in a zkVerify chain. And after a while, basically when enough time has passed or enough proof has been sent to zkVerify, zkVerify produces a so-called attestation, which attests the correctness of a set of proof. Technically, this happens via a Merkle membership proof. So the attestation, for those of you who are familiar with Merkle trees, is just the attestation is just the Merkle root of the Merkle tree of basically of the statements of these proofs. Okay, then when this attestation is produced, there is basically a relayer which takes this attestation and posts it to a smart contract, to zkVerify smart contract on Ethereum. So on Ethereum, on each, not only on Ethereum, but on each EVM which we support, which is Ethereum, at the moment only in testnet, but there are also, we support also other EVMs such as Gobi, which is Horizon EVM, and then also on ApeChain or Arbitrum testnet, and more will be added in the future. And okay, then, this attestation now has been posted to the zkVerify smart contract. Then, basically, the Polygon CDK has to trigger another transaction it must post to the zkVerify smart contract basically the Merkle proof of inclusion. So to ensure on-chain that the proof which has sent to zkVerify has been verified and has been posted to zkVerify smart contract. So at a high level, this is the workflow. And now we will dig into the code which actually performs all of this action. So it should become everything more clear. Okay,
so Luca, this is a general model that people can use to have the smart contract have their verification done on zkVerify instead of natively on Ethereum or an EVM. And so that gives you the ability to not only do a lower price, but also use a different type of zk proof. So this was I know this was the first one that y'all did, and then also did one for zk Sync Era for the Boojum. And so we still are talking to projects that want to do their own zk rollup using this way, because you're right, it's, to me, price is always part of the design factor. And so by being able to have a lower price by sending the receipt of the verification to the layer one, that's a much less expensive transaction than doing the transaction of actually verifying the proof using the BN254 curve pre-compiles on Ethereum. So this is still this is a very valid system. Polygon's not doing this; they got their Polygon ag layer. But individual projects that may want to do zk rollups using the Polygon CDK or the zk Sync Era still might want to do this, and they should talk to us about it.
Yeah, definitely.
Okay, thanks.
Okay, let's jump into the code. So basically, we see the three main building blocks of our application. So there is what I call the app, which is the, let's say, off-chain logic, which actually generates the proof and sends the proof to the zkVerify chain, listen to the relevant events emitted by zkVerify, and which is necessary to retrieve all the information that must then be posted instead to the EVM in order to make the EVM smart contract aware that this proof has been verified on zkVerify. Then there is the circuit, which actually contains the zk logic, basically. And then there is the contracts, which contains the EVM smart contract. So I think we can start from the circuit, which for most zk apps, maybe it's the most complex part. But for us, it's very simple because, as I already said, the logic is very simple. So as I said, I've used the Grok16. So I developed the circuit in the Circom language. And yeah, code is really simple. And okay, it's just this factorization, which can be configured for different n. Here we configure it with 42. And this circuit basically only makes sure that, okay, takes in input two signals, which are private. So we don't reveal actually the factor A and B, and ensures that the product of A and B is equal to n. And okay, here we take another public input address, which is, doesn't appear in any other constraint, but it's revealed as a public input. So this is, let's say, a trick which can be used to ensure that your proof isn't exploited by other people which didn't generate the proof, but would like to reuse it. So because we will see later in the app logic, actually in the smart contract logic, that we require that this public input is set equal to the address of the sender of the transaction. So this ensures that if you generate some proof and send it on chain, then this proof, of course, becomes public. And if we didn't introduce this trick, then anyone could exploit it for their own. And so, yeah, this is the only, let's say, tweak in our circuit. But for the rest, yeah.
I got a question about this. So we do have some people that join the hackathon that don't have as much experience with generating zk proofs. So it looks like you're using the Circom domain-specific language here, and factorization is a native method in Circom. I'm sure there's a number of other native methods as well, but this seems like a pretty straightforward way to generate a zero-knowledge proof in a basic way. I bet there's a bunch of other examples out there too. So was talking with Gaylord at ZK Hack, and we're also co-sponsoring something with ZK Hack right now. And he's had a lot of experience bringing people into the ZK space. And his recommendation is to start with a really basic circuit first to kind of get your feet wet with ZK proofs, and then you can always make it more efficient or more performant later on. Start with something basic, and then you can always make it more complicated. So to me, as a basic software developer, this looks pretty straightforward. This looks like something I could do that wouldn't be too scary. I'm sure that you can make things a lot more complicated in Circom, but I really appreciate you sharing this example here.
Yeah. It's always a wise choice to start simple, and it's always possible to add additional complexity. It's more
Yeah, so instead of
difficult to
factorization,
do
you
the
compare
reverse.
if maybe A is bigger than B or if A is equal to B. You could probably do that too, right?
Yeah.
Okay.
Actually, yeah. Okay, just a side note for those of you who are not very familiar with circuit. Actually, even this is ZK tech is quite strange, and for example, even ensuring that A is bigger than B is not that easy. I mean, Circom provides some, let's say, abstraction which makes it look easy, and you can do that in a line of code. But under the hood, this requires, for example, doing what are called these bound checks, basically. And this requires introducing in the circuit a lot of constraints. So yeah, definitely getting into the ZK space can be quite intimidating. But okay, now things are starting to change in the sense that besides circuits, which can be quite difficult to write properly, are starting to appear also zkVMs, which are much more user-friendly. One example is RISC-0, which allows you to write your code, your ZK logic in Rust, so plain simple Rust, and then magically build a ZK proof out of that without having to worry about all the circuit writing stuff, which can get complicated quite fast.
Oh, I'm glad you mentioned that. I was thinking maybe we should have a live stream next week, but maybe we do something where we show people how to build something really basic in RISC-0, because we have a native RISC-0 verifier that verifies the RISC-0 Stark proof, and we're one of the very few places where you can publicly online verify a RISC-0 Stark proof. So I'm glad you mentioned that. Okay, that's something that maybe we want to show in the future. Sorry to take you off track. Please continue.
No problem. Okay, so this is the circuit. Here, Groth 16 requires to also requires to run a trusted setup before being able to generate and verify proofs. And here I've included a little makefile which allows to run all the necessary steps of the setup just by running make call. This requires to install snark.js as a dependency. But then it's pretty straightforward. But if you want to try out the application, you don't need actually to rerun the setup, because I've already committed the final result of this setup here in this directory. So no need to rerun. But of course, if you are curious, you can do it. Okay, so that's it for the circuit. And we pass to the more, let's say, beefy components. So here we take a look at the contract. Okay, so here is our contract. Just let me close this. Okay, so this is our ZK factorization contract. So, okay, now I'd like to spend, no, let's do that later. So here, okay, hold off for this line for some minutes. We will get back here in a few minutes. So here we just see, okay, this contract has these two immutable variables, which are initialized during contract deployment, which are the address of the zkVerify contract. on the chain you are interested to deploy on, and the hash of the verification key of the circuit. Okay, so as those of you who are familiar with Grot16 know, a proving system has the concept of a verification key, which basically encodes the statement which you are proving. And here, if we go back to the circuit directory, it's this, for Grot16, it's this structure. For Grot16 is quite small, the verification key. And the smart contract needs to know which verification key you are using, because it needs to ensure that you are proving a specific statement, not any general zk proof. And yeah, you, in technical lingo, you must commit to this verification key through its hash. And so we must compute beforehand the hash of our verification key. So here I have included a small utility which actually register to zkVerify the verification key and gives back its hash. So we can just run this script. Okay, sorry. So okay, this is JavaScript, so we use Node to run it. Oh, yeah. Sorry, wrong. Of course, being a live demo, things are bound to go wrong. So okay, I didn't specify the account. Yeah, sorry. Because, yeah, I did some last-minute refactoring which broke things, so I can... Okay. This should fix it. Okay. Okay, so now we have submitted. Here we can see the code while we wait. So here, basically, we are using zkVerify JS library to interact with zkVerify chain. For those of you who have already followed the previous live stream, Steve already introduced this library. So here we are just reading the VK from the file that we saw before. So inside the circuit setup folder, and we are establishing a session with zkVerify. Since okay, here we are using the URL of the RPC for zkVerify, and we are passing the seed phrase of a wallet which has some funds on zkVerify. And then we send the the verification key with the register verification key for the Grot16 proving system. And yeah, we pass the VK. And then we await the transaction result. And this, among the other things, this gets back the statement hash, which is basically the hash of the verification key. Okay, so this is this particular value. And okay, so we know now that the hash of the verification key, which we want to use. And so this was a little detour to say that we should include this value here inside the environment file. No, sorry, inside the other environment file, so the contracts environment file. Okay, here we have copy-pasted the verification key hash. Okay, so back to our contract. Okay, so now, okay, we know the contract, the zkVerify contract address, the VK hash. Here we are defining, okay, the event which we emit if a successful proof submission happens. In the constructor, we pass the values, the actual values of the address of the zk contract and of the VK hash, so that our contract knows how to interact with zkVerify and which particular statement we are proving. And then there is, let's say, the main method of the smart contract, which is this method, which, okay, the name says it all. And yeah, okay, so here I think I can close this tab. Basically, here we are performing, so as a first step, we are actually calling this internal method, which actually verifies that a proof has been posted to zkV. We will see later the internal of this method. And if this check is successful, then we just emit, okay, we set, let's say, the result in a mapping, and we emit the relevant event saying that the sender of the transaction successfully submitted a proof. But of course, here for an actual dApp, it's where the interesting stuff happens. For example, a zk app could mint an NFT, for example, or do some other cool stuff. Okay, but here basically we see the internal of this verified proof has been posted to zkV. So this method takes as input an ID of the attestation, the so-called public input of the proof, and as we saw earlier, this public input is just for our case, the address of the sender of the transaction. Then, okay, as I was saying, the attestation is actually a Merkle root of a Merkle tree. So to be sure that a proof has been included in the attestation, we must provide the so-called Merkle path. And then there are some additional details which must be known in order to check the Merkle proof, which is the total number of leaves of the tree. of the attestation tree and the exact index of our own proof inside that tree. So, okay, important things is that these four parameters, namely attestation ID, Merkle path, leaf count, and index, are something which can be retrieved from the zkVerify chain after we have submitted our proof to it. Instead, this public input is actually recomputed by the smart contract, and this is a typical pattern in zk apps. So in zk apps, oftentimes the public input is independently recomputed by the smart contract. In this example, recomputation is straightforward because the public input is just the sender of the transaction, the address of the sender of the transaction. Okay, so here we see actually how this verified proof has been posted to zkV is implemented. So, okay, this is something, okay, this is the most tricky part of the contract because zkVerify treats public input in a big endian format. Instead, in Ethereum, the format is little endian, so we must switch the endianness of the public input. And this is performed by this change endianness method, which is here. It's a bit technical and it's the most tricky part, but it's just a technical detail. So basically, encoded input is just the proper encoding of the address of the sender, in our case. Then we must compute actually the so-called leaf of which is a hash of the statement we are verifying. And this is composed, you can find the details inside the zkVerify documentation. And basically, it's just the catch-up hash of the proving system ID, which specify which particular proving system you are using. So in our case, proving system is graph16, and so it's just the catch-up 256 hash of the graph16 string. Okay, we concatenate this with the vk hash, which we computed before, and which is saved inside this immutable variable in the smart contract. And the hash, and we basically append also the hash of the encoded input. All of these is concatenated together and hashed. And this is basically a unique identifier of the statement of a particular proof. You see, we are basically saying that, okay, what we are proving is proving with this particular proving system, this particular statement encoded by this particular vk, which has this particular hash, and that the input is this particular public input. So we are fixing all the variabilities. And later we call actually the zkV contract. And in particular, we call the verify proof attestation. Also, this you can find documentation in zkVerify repo. And okay, now basically we just passed the attestation ID, Merkle path, leaf count, and index, which was passed. and here the leaf is computed here. And if this method returns true, it means that the proof was successfully verified on zkVerify and sent to the smart contract, to the zkVerify smart contract on Ethereum. So here we just decode the result and return. Okay, so it was quite involved, but hopefully this is more or less clear. Sorry, Rolf, I cannot hear you.
I had myself muted. I said this was great. I think you did the whole circle of starting in the smart contract, sending the proof, verifying it on zkVerify, coming back to the smart contract. Are there other important things that people should know when they're developing?
Yeah, basically, I mean, we saw the smart contract, and we already explained a bit the logic behind all this back and forth between the client and the chain, the two chains, basically. And here is just the piece of code which actually performs all of these orchestration. So here is the so-called app code, which in this case, the app is just a simple script in JavaScript. So, okay, going to the important stuff. Okay, here we see, okay, dependencies, we use, again, zkVerify JS library for interacting with the zkVerify chain. Then we use the ethers library, but you can use the library of your choice for interacting with the EVM chain instead. And for generating the proof, we use the snark.js library, which allows generating Groth16 proofs. So, okay, we can take, let's say, make a quick tour of the code. So, okay, here we are just loading some useful info from the environment file. In particular, the URL of the RPC for interacting with zkVerify, the seed phrase of an account of zkVerify, the RPC URL for interacting with Ethereum, the secret key of an account on Ethereum, and the address of the zkVerify contract and of our own app contract. Okay, here we see that with snark.js, generating a proof is quite simple. Of course, this program takes as input the two factors, A and B, and generates a proof that A times B is equal to 42. Okay, so here now we have the proof and the public signals. Here we retrieve the VK from the file, and we start a session with zkVerify using zkVerify JS library. And here we send the proof that we generated, so proof, public signals, and VK. We send them to zkVerify, to the Groth16 verifier of zkVerify for verification. Here is a modifier which makes the method wait for the actual publication of the attestation by zkVerify. So when this method will return, the relevant attestation will have been published on zkVerify. So to keep track of of the stage the transaction is at, we just listen on some events emitted by zkVerify. In particular, we listen when the transaction is included in block, when it's finalized, and possible error which arise during the transaction life cycle. And yeah, as I was saying before, after this method returns, the attestation has been published, so we can retrieve the ID of the attestation, the leaf digest that we saw how it's computed, this leaf digest inside the smart contract, and via another RPC call, the POE, which means proof of existent RPC call, we also retrieve the details about the Merkle proof of inclusion of our proof, our statement inside the attestation. So we can retrieve the Merkle proof, number of leaf, and leaf index, which are all details which are needed by zkVerify smart contract for actually performing his checks. So now that we have all the, at this stage, to recap, the proof has been sent to zkVerify, verified by zkVerified, and some events have been emitted to which contains basically the details of the attestation, which contains our statement, and the Merkle proof, which allows to show that to the smart contract that our statement was included in this particular attestation. So now we have all the details which are necessary to actually interact with the EVM side. So we use the ethers library to set up a session with the EVM. So here we define the API of the contracts we are interested in interacting with, namely the zkVerify contract, and in particular we are interested in being informed on when the attestation, of which we called later, which we spoke before, was actually posted to Ethereum. And instead, for our own app contract, we are interested in invoking the proof you can factor 42 method and being informed of successful proof submission. So here we just set up everything, and here it's the interesting piece of code. Okay, so here we just wait for the zkVerify contract to emit the event attestation posted with the attestation ID which we are interested in, which was actually computed here. So here we keep listening to event, and as soon as this event attestation posted is emitted by the zkVerify smart contract, then we can send our own transaction to the app smart contract. So we invoke the proof you can factor 42, passing in all the details that we retrieved before in a zkVerify chain. So the attestation ID, Merkle proof, number of leaf, and the leaf index. We recall that every one of them was retrieved by either this call to zkVerify or this other one. So, and then after we submit this attestation with this transaction, we just wait for our contract, the app contract, to emit the successful proof submission with our own account. Okay, so time is running by, so we make a quick demo of this actually running. So okay, maybe I maximize. Okay, of course, I must pass the our well-kept secrets, A and B. So we pass A, the first factor, equal to 7. Okay, so, transaction has been submitted to zkVerify, and here we get the transaction hash. So now we wait for finalization of the transaction. Okay, transaction has been finalized in this particular block. Okay, now we are waiting for the attestation of which contains our own proof to be actually generated by zkVerify. And this could take up to 1 minute.
Okay, so the process that we're waiting for, because obviously 6 times 7 is 42. So we should be able to get a positive answer here.
Hopefully, yes.
Hopefully, yes. And maybe after this, we can do a test of seeing what happens if we send it a bad set of factors. But I know from what you've explained to me before, this sends it to zkVerify right away. And one of the validators, which runs all the verifiers on it, verifies it. Then when 2 out of 3 of the validators agree that it's true, it gets posted to the blockchain. And the blockchain has a 6-second time, so there's a new block every 6 seconds. And then we have an attestation bot that gathers together so it's on the blockchain after basically about 6 seconds, if it's correct. And I know that right now, y'all have the attestation bot. You can bring a bunch of things. Oh, there it is. So you probably have it set up to go every minute or something like that. It can be set to every block. It can be set to when we get 127 or 2047 proofs verified. We're still in testnet. We've been in testnet since March. And I've been wanting you to do this the demo since March, so I'm really excited. So tell us what we're seeing here.
Yeah, okay. So basically all the workflow executed correctly. So yeah, as I was saying before, proof was generated, of course, even though no log were printed. Then this proof was sent to zkVerify. Since the proof was correct, the transaction was accepted. Then the blockchain finalized the transaction, and after the transaction is finalized, then periodically an attestation is produced, which contains basically our proof. So here we get all the details of the attestation, so its ID, the digest of our statement, and details about the Merkle proof. So with all these details, we are able to actually invoke our smart contract. So basically, we waited for also the attestation to be not only published by zkVerify, but also posted on Ethereum by this attestation bot. And as soon as that happened, then we sent our transaction to our app contract. And yes, our app contract basically queried zkVerify contract saying, hey, did you see an attestation containing this leaf digest? And here is the Merkle proof, the details of the Merkle proof that you must know in order to be sure of the inclusion of this leaf digest inside the attestation. So the zkVerify contract answered yes, and so the app generated this event that of successful proof submission and closing the loop, basically. Of course, everything can be checked on the block explorer of both the EVM, so on Etherscan, and of zkVerify. Don't know if we have time for that.
So, Luca, we got all the time in the world. Everybody wants to see this demo and build Web3 apps to do zkVerify. So, um,
Okay, sure. So let me just okay, so here we should be able to retrieve, for example, the transaction sent to our contract. Okay, so this is the details of the transaction. So you see that we call the prove you can factor 42 method, and this emitted the successful proof submission. And I think in internal transactions, we can see that actually this transaction interacted with another contract, which is actually the zkVerify smart contract. So for performing proof verification, it basically queried the zkVerify attestation smart contract. On the other side, we can also see on zkVerify Block Explorer. Okay, this is the old Block Explorer.
got to use the new fancy Block Explorer.
Yeah, I don't remember the URL.
I don't remember the URL. Gosh, I will look it up though. I'll look it up. Just give me a sec.
Yeah, by the way, here is the link to all the interesting documentation for zkVerify. In particular, in this zkVerify hub, you can, for example, see all the contracts of the attestation contracts on these chains, which we support, the URL of the RPC for interacting with zkVerify, and okay, here the proof it's the proof explorer, but okay, here is the block explorer also.
Oh, good.
New fancy block explorer. Okay. Okay, here we can see that actually our transaction for zkVerify was for a GROT16 where do we, okay, for the GROT16 verifier with the BLS curve and with this particular decay. And this is the actual proof. And this is the public input, which actually was the address, the EVM address that we used for sending the transaction to the EVM. Yeah, that completes basically the loop. So I don't know if there are questions.
So obviously on these live streams, one of the reasons we do them is so people can ask questions on x.com while we're doing live stream. Of course, people are welcome to ask questions later on in the Discord or the Telegram. And one of the things that we want to be sure is that everybody who's entering the hackathon is getting the support that they need. So please, if you're developing and you got questions, if you want to ask your question publicly in the hackathon channel, please do. You can go to our zkVerify Discord. You can do a ticket for a private discussion. We have some Telegram groups set up with some developers already where they're asking specific questions. One of the things that like I said, I do very basic development, is to try to figure out like what's wrong with my code, because a lot of times my code doesn't work. Do you have any recommendations for people how to troubleshoot different aspects of this? That's probably a broad concept or thing, because I mean you have a great JavaScript example here. It brings in the Solidity contract, and it uses the zkVerify JS that Steve Rushby went over a couple of days ago. So I think this is beautiful. You said all this is going to be published, this working version, on the zkVerify GitHub?
Yeah, it's already published.
Nice.
It's already there if you want to take a look. And yeah, I mean, here I think that, yeah, of course, definitely if you find some blocker or something unclear, definitely reach out on Discord. You will find some developer able to help you out. And in particular, I think that one of the rough edges that are still there, we are working on it though, is in this particular part of the code. So in the smart contract, actually, in computing, actually, the properly encoding the public input can be tricky. So in this case, it required changing the endianness of the input, which, okay, entails this strange-looking piece of code. So it's the trickiest part. We are actively working on making it much easier. But in the meantime, if you find some difficulties here, just reach out on Discord and we will be able to help you.
I think the biggest, most important thing is a working example. This is wonderful. I think we're about ready to wrap up. Luca, this was great. I really appreciate you going through this, and I'm sure a lot of the developers in our hackathon are too. Any final words before we finish up?
Yeah, I mean, of course, this was all the, let's say, architecture that you need and all the pieces. Now you just need to fill in the interesting stuff.
Yeah, absolutely. No, this is a great framework. Thank you very much. Well, I think we're going to go ahead and end up here. We may end up doing another live stream on how to use a ZK virtual machine. There's a number of different ZK VMs out there. We want to have verifiers for all of them. Most of the ZK virtual machines, they'll create either like a Plonky 2 or a Plonky 3 proof or a Stark, and then they'll wrap it in Groth 16 and send that wrapped Groth 16 to an EVM. Of course, zkVerify is not an EVM, and we got verifiers for everybody. That's our plan. So instead of taking the extra computation, the extra time to send that zkVM, to wrap that zkVM proof into Groth 16, you just send it to us as a Stark or a Plonky 3 or whatever. So, all righty. Well, thanks again, Luca. We're going to wrap up and look forward to the next one. This was great. Thank you so much.
Bye, everybody. Thank you for joining.
Awesome. We're done. That was awesome.